a global integrated assessment perspective. And I will hand the word to my colleagues who will talk a little bit about some of the key results. We will present a few selected highlights on two main research questions. The one is the question on how to quantify the differential climate change impacts on different groups with two examples. And then we will discuss a little bit results on global climate policy and inequality, and how we can alleviate also negative effects for inequality which arise from mitigation. The first example is on income-specific vulnerability to tropical cyclones in the United States, and I hand the word to Thomas Vogt from PIC.
Thanks, Franziska. I will provide a very brief teaser of results from a method implemented by a master student, Jan Hassel, who cannot be here today. This approach takes an event-based perspective on climate in order to be able to include the effects of extreme events in a more explicit way. We consider this to be complementary to other approaches like the one that our colleague Peron will present in a minute. These other approaches use continuous time series of abstract meteorological variables, such as temperature averages or precipitation totals. Instead of what we do, we use singular and geographically rather localized extreme event data. So far, we have applied the concept only to tropical cyclones or hurricanes in the US, but it is in principle possible to apply this also to other regions and to other extreme event categories such as river floods, but I won't go into this now. In our study, we calibrate the vulnerability, that's the point, like the vulnerability of 5 different US income groups to hurricanes according to 3 main input data sets. Firstly, we have 25 years of damage reporting on the US county level, so in the subnational data. We have gridded data of economic asset distributions throughout the US on 10-kilometer resolution. And thirdly, we have hurricane wind fields on that same 10-kilometer grid. And the most important methodological ingredient is that by the term vulnerability, we here refer to how many of those economic assets are destroyed when a hurricane hits the grid cell with a particular intensity. And in this sense, in this context, we express the intensity in terms of wind speed. So we calibrate that relationship for each of the 5 income classes in such a way that the reported damages are reproduced as good as possible when overlaying the economic asset distributions with the hurricane wind fields. Using those calibrated or empirical, you could say, vulnerabilities, we computed several metrics that are supposed to illustrate the differences between the 5 income groups that we found. So we expect that this methodological tool is much more powerful and emerge in all kinds of future applications, for example, in macroeconomic models. But for this presentation, I will stick to these indicators. So in general, the most important result is that the vulnerability does decrease with increasing income, as you see in this graphic. But it's not easy to quantify this in a meaningful way. So for example, in this graphic, you can see that, for example, if everyone in the USA was as vulnerable as the poorest 20%, the hurricane losses, according to our model, would be more than 90% higher. And next slide, please. On the right, you can see that if everyone was as vulnerable or as resilient as the richest 20%, the hurricane losses would be more than 40% lower. And we have some more statistics. Next slide, please. So compared to an approach with an income-independent vulnerability, which already existed in the literature, the lowest income classes losses are 30% higher, and accordingly, like the higher income classes have lower losses. So it's more like a redistribution compared to models from the literature. And finally, we also try to learn something about adaptation potentials for the lower income groups. So speaking within the logic of our model, approximately 25% of the total damages could be avoided by increasing the resilience of the lower 2 income classes to the level of the 3rd income class. And I leave it at that at the moment. And with this, I hand over to Peron, right?
Yes, thanks, Thomas. Yes. And this was not a global example, but we included this because this extreme event category is, of course, one of the categories which is most important also for adaptation and for inequality effects. But now we will move to the global level with Peron.
Okay, yeah. Thank you, Franziska and Thomas. Since the earlier study of Berke and colleague, we actually have a fair understanding of the impact of temperature change on country level income growth. So as you can see on the left-hand side of this image, Berke finds a nonlinear relationship between GDP growth and GDP growth per capita, and peaking about 13 degrees. So countries that are below this temperature optimum, like Germany, UK, and France, warming brings a positive impact on GDP growth. And countries that are on the left-hand side, like Indonesia, India, and Nigeria, warming brings negative consequences. So this is quite fairly understood, and projection also further into the future, which they did, also shows that the countries which are hotter and tends to be poorer as well are severely impacted by additional warming. Since then, I mean, a number of studies like Diefenbach and Berke have also confirmed this, that actually climate change has increased inequality between countries. This is quite fairly understood. However, the effect of climate change on within country income inequality is poorly understood and limited. Next slide, please. So in this study, we try to look at the differential impact of temperature change on different income groups. So here we evaluated 10 different income groups, and our main identification strategy actually relies on observing how income growth is impacted by year-to-year variations in country level temperature changes. And here we'll report, we also employ the panel fixed effects regression approach. And in here we control for income growth specific fixed effects, year fixed effects, and also control for slowly evolving factors within countries, such as demographic shift, evolving political institutions, and also trade liberalization. We also tried out a different model specification, slightly different modification by varying time trends, for example. Also adding additional controls like controlling for population growth, inflation, globalization, trade and finance as well. Also trying different complete data sets, sort of using population weighted data, area weighted data, and also different model specifications such as the calculus events specification. And the results were kind of robust across all these specifications. So on the left-hand side, we show the marginal effect here as the effect of a 1 degree increase in population weighted mean annual temperature on income growth for the two income groups, by bottom 10% and at the top 10%. And here what we can see that the lower end of the temperature spectrum, the effect of temperature change on the income growth of the bottom 10% is larger than the top 10%. I mean, this is logical because lower income groups are more vulnerable to climate change, or they work in more vulnerable sectors like agriculture and also outdoor activities. So beyond or below the optimum, the effect of temperature is positive for them. On the higher end of the temperature spectrum, we find a reverse, that additional warming reduces significantly the income growth of the bottom 10% compared to the top 10% of the income distribution. And here we try to map up the country level change in income growth per 1 degree in temperature for also the bottom 10% and the top 10% of the income distribution. And as we can see, there's a strong latitudinal dependence, so warmer countries tend to be severely more impacted compared to colder countries. And also the effects are also more pronounced for the bottom 10% in terms of gains and losses compared to the top 10% of the income distribution. So with that, I end here, and I hand over back to Franziska.
Thank you, Peron. So these results are quite important because if we now want to really quantify mitigation and damages together and their distributional effects, in principle, so far we do not have robust quantitative input on, especially on the damage side. That's why these advancements are so important also for the integration part, which I'll talk about now. So by integrated assessment, what we mean is that we have at the core projections on socio-economic development, on technological development, which results in emissions and which can be combined with emission targets, with temperature targets in a sort of looking at climate policy. But then we also want to close the loop of looking at the effect of these emissions on climate change, on the damages, and how that again feeds back into our socioeconomic system. So that's what we call integrated assessment. And we now bring in the component of distributional effects on the mitigation side. So how, for example, increased energy expenditures affect inequality, and on the damage side, how different income groups are affected differently by damages. We use two integrated assessment models. They are complementary. That's why it's very nice to have two in the project. The REMITE model, which is a model which has a very detailed energy system, and so therefore can much better capture, for example, inertias in the energy system on how quickly mitigation can also happen. And on the other hand, the NICE model, which is more aggregate and therefore more versatile in also studying many sensitivity experiments. But they both have different regions, different large-scale world regions. They both include damages and mitigation and have this sub-regional income groups, so the distributional effects also within the world regions. And we apply them studying only one socioeconomic scenario. This is sort of the minimum we could manage, but we look at different climate policy targets. We can also do cost-benefit analysis, but that's not what we will present here. And then we will look at the redistribution possibilities of carbon price revenues and how that can be used. And in a first type of result, I would like to highlight what we rarely do, which is really the benefits of climate policy, which we now can address in two components, in the component of GDP and in the component of inequality. So what we see here is, first of all, just a baseline scenario where all we see is damages. If we include damages according to our current trend, 3 degrees warming, we have losses of GDP by the end of the century, and we have increases in inequality indicated here by the Gini index. If we now do climate policy, we have, of course, what we well know, in the near term, we have losses, we have costs from mitigation. And this mitigation also increases inequality. It's a little hard to see with the scale here. But what we usually not show very explicitly is that in the long run, we have benefits because we reduce the damages we have in the baseline run quite substantially by the climate policy. That's why we do it. But normally we do not really show these benefits. So we have benefits in terms of reduced GDP loss compared to the baseline because of lower damages. And we also have benefits because we have now actually not an increase in inequality resulting from damages, but actually we can improve on that because we avoid the damages and we avoid their regressive effects. Of course, these results depend strongly on the country, and they look different if you are a developed countries or a country which is maybe focused on fossil fuel extraction and export, or a developing country. In the near term, we have losses for all of them. The magnitude is quite different, and we also have increases in inequality, certainly in Europe and in the Middle East here. In the long run, however, we see these benefits in all the regions. And the second the second result I want to show real quick is that including inequality into our integrated assessment really also has an effect on the emission pathway. So this is the global emission pathway for a 2-degree scenario. let's focus on that first. We can see the green line is what we usually have when we don't include inequality. The blue and the red is when we do include inequality, and we see that there is an increased near-term ambition for mitigation when we include inequality. So that's really important. It really gives us another incentive to increase our ambition. And also in the 1.5 degree scenario, of course, there we are much more constrained because we already reduce very, very strongly in the near term. But even there, we see this tightening. So there's an effect on our optimal mitigation pathway. And with that, I hand over to Stéphane.
Yeah, thank you. So I will present other results from one of these integrity assessment models that are results from the NICE model. These are results on the redistribution of the carbon tax revenues. And so what are the consequences of that in terms of redistribution? So we know that a global carbon tax or carbon tax in general can be a good tool for mitigation, but as we mentioned already before, it's not very well accepted. And one reason for that is that it raises a lot of issues in terms of justice and inequalities between different income groups. So actually, when we do some redistribution of the carbon tax revenue, it's already known that there can be some benefits even in terms of inequality, and that the carbon tax can help in that direction to alleviate inequality and mitigate a little bit those negative effects that prevents the adoption of carbon taxes. So what we do in the work that I will present is to try to link the redistribution of the carbon tax to the current discussions on the loss and damages and the policy discussion around that, and in particular on some proposals that have been made at COP27 to use a global carbon tax that actually is not as ambitious as the one I will mention. It's only typically on airplanes tickets or something like that, but to use this carbon tax to fund something that will help with loss and damages. So we try to implement something like this by assuming that we have a global carbon tax in the NICE model and to redistribute the revenues according proportionally to damages. So to have a rule that says that the redistribution will be proportional to damages. And so we look at the effect of that on inequality and poverty, and that's the next slide, please. So this is the first kind of results that we have, which are on inequality. So we compare actually these different kind of policies. So this is a climate policy with redistribution of the carbon tax, and we compare that to a baseline where there is no climate policy. So what you have on the graph are the changes in terms of the Gini index of inequality. So you have a decrease in inequality in all these cases because we are redistributing the carbon tax in a lump sum way in many of these cases, which explain why we have these impacts. And you see that there are different kind of scenarios, regional, global, and proportional to damages, which correspond to different way to redistribute. So you can redistribute the tax at the country or regional level, or you can try to do something more ambitious and go at the global level, or do what I mentioned before, which is proportional to damages. So what we see here is that, of course, some regions benefit a lot of this kind of scheme, especially sub-Saharan Africa in the example that we have here. Even if in all countries, more or less, we see a decrease in inequality when we do that. Also, what is interesting, I think, is that there is a very when we do it at a global redistribution lump sum is very similar to what happens with a proportional to damage scheme. And this is also true for poverty, which is the next slide. So on the next slide, you will have results on global poverty for these different kind of scenarios. So what you have here is the number of people who can go out of poverty thanks to a redistribution of a global carbon tax. So you do the global carbon tax, you redistribute, and some of the people who were poor before, they're not poor anymore. So the definition of poverty is it's the World Bank definition of absolute poverty that we use here. So what we see here again is that there are large benefit of redistribution of a global carbon tax to reduce poverty in the medium run. So it's like 70 million of people. So it's very large for the global or proportional to damages cases. And so if you do this redistribution, there are these very large benefits in terms of poverty that you can achieve. in the medium run, that there may be actually some problems, because at some point you don't have any more carbon tax because you are fully decarbonized, and in that case the cost of the climate policy can be negative. But in the short run, at least, this can be a very powerful tool to reduce poverty. And I hand over to, I don't know, Marie or Simon, I'm not sure.
Yes, thank you. So our final highlight focuses on looking at different types of damages. These results used aggregate damages, everything, all the damages just added up. But of course, it makes a difference, the channel how these damages act, and they have different distributional effects. And so the last highlight, we'll discuss that a little bit.
Yeah, great. Good afternoon, everybody. My name is Peron Feindt, and I present research that I conduct together with Marie Young-Brun on disaggregate damages and its effect on inequality, but also on the social cost of carbon ultimately. And the motivation of this research is that we have seen by the work from Thomas Vogt, but also from Peron Collins-Sowah, that the distribution of climate impacts depends on pre-existing inequalities. Two examples here are that heat stress hits outdoor workers more, and the second example being that poorer households tend to live in more flood-prone areas. So two dimensions, more labor affected dimension, and the other one more related to wealth, income. So far, most climate policy models neglect the heterogeneity in these income channels, and then in the next step also the inequality in these two dimensions. Next slide, please. And in order to model the inequality in damages, we first have to decompose the income inequality along the capital and labor income dimension. To this end, we use raw data, national raw data, first for the labor income share and second for the wealth Gini index. This national data is then used for aggregation to the 12 regions that our model, the integrated assessment model, NICE, features, and also used for the calculation of the income channel for each of the income quintile in each of the regions. We can then disentangle damages on capital and labor income, but also let damages fall depending on income inequality. And the more disproportionate damages fall, the more unequal they fall, the more heavily they fall on the poorest income quintiles. Next slide, please. And let me briefly present some preliminary results. The main takeaway message is that it matters for global and regional inequality if damages on capital and labor are considered in this kind of global models. Let us look at the plots on the right, where we have in both plots a line for the baseline scenario. This is a scenario where damages fall completely on global output, the usual case in these global models. And the second case, the dotted line, is the line representing a case where damages fall 50% on labor and 50% on capital. And on the right scenario, these damages are distributed proportionally, meaning that they fall on quintiles depending on the income share in capital and labor income. On the left plot, they fall more heavily on the poorest. And as you can see now, the two lines, the baseline and the line for the damages on labor and capital, they diverge. This line represents the global consumption Gini. So the global consumption Gini does not decrease as it does with damages completely on output. If damages are assumed to fall on labor and capital and fall more heavily on the poorest, global consumption Gini decrease comes to a halt in the second half of the 21st century. So we see less reduction in global inequality, which is mainly caused by increases of within region inequality. And this leads ultimately to a higher social cost of carbon, which implies stronger mitigation can avoid increases in future inequality, but also improve welfare levels. Back to Franziska. Thank you.
Yes, since we are already over time, I don't really want to spend too much time to conclude, except that maybe to really stress that what we find here is that including inequality into these assessments really motivates more stringent climate policy, especially in the near term. And it also supports policy design for adaptation and for loss and damages to really quantify these things also for different income groups. We do not take into account adaptation yet in this modeling, and that would be one of the crucial next steps also for this type of modeling. With that, I would like to end. Since we are